So far, we've done examples where there's always horizontal asymptotes. In the horizontal asymptote video, you saw how that there's not going to be a horizontal asymptote for every rational function. So let's talk about in this video how we're going to sketch those, what they're going to look like. And here would be an example that did not have a horizontal asymptote. Reason it doesn't have a horizontal. The reason it doesn't have a horizontal asymptote is because the power degree in the numerator is greater than the one in the denominator. So if I'm thinking about what happens as I approach infinity, the top x squared kind of dominates and the bottom x dominates. And if I reduce that, I get x. And if you were to figure out the limit as x approaches infinity, we'd see it goes to infinity, negative infinity if x is approaching negative infinity. So, right. So here's what we need to do. All right. We're going to start by doing some long division. What we're going to do is we're going to break this down into two pieces: the rational part and the regular equation part. Okay, so we're going to do some long division here, and so that'll go in x times. So I'll have x squared minus x. Subtract it. Oh, that nicely cancels, and I just have a remainder of 3. So this one was this is as easy as it gets in terms of the long division. So we get this. My remainder is 3. So these two things are equivalent to each other. And so now let's do the same thing. So the domain restriction. When I say same thing, the same thing that we've done for all the other examples. Domain restriction, x equals 1. Limit as x approaches 1 from the left. Well, okay. What do I use? Do I use this one or this one to? Do I use this one or this one to calculate it? I'm actually going to use this one right here for myself to calculate it because I thought that might be a little bit easier. But if you wanted to, you could use this. The problem, I guess, with using this is actually, since we're probably approaching infinity, maybe let me try this one. So if I plug it in, this is just a 1. What's this number approaching? This number is just approaching a 1. And for the rest of it, it's going to be 3 over, and then 1 from the left is like 0.99999. 0.99999 minus 1 is a negative small number. Remember, this is going to give me negative infinity. 1 minus negative infinity, still negative infinity. So that tells me my graph is going to be going down as I approach from the left. The limit as x approaches from the right of the function. Okay. Once again, limits are trend analysis that we're looking at here. Okay, we're just looking at what's happening. So if I do that, right, this x is just approaching 1, and then the rest of it, 3, and then 1.0001 minus 1. Well, that's positive small number. So I get 1 plus infinity, so I have infinity. Okay, so I can see what's happening here. This is definitely an asymptote, so I have a vertical asymptote at x equals 1. Okay, and if I'm thinking about my graph of this, okay, as I'm approaching from the left side, it's going down, and from the right side, it's going up. So I can kind of put those arrows in place for myself. I forgot to do my intercepts on this one. I like to do that right after I do my domain restrictions. Let's just think about that. Intercepts, which one you pick is kind of up to you. If I'm going to use I'm going to get the y-intercept, I plug in 0, and it gives me negative 3. If I want to get the x-intercepts, that means you're setting this equal to 0. So the x-intercepts can be kind of tricky for this one. They're doable, but that just means you're basically looking at your denominator equaling 0. I'm going to have to use the quadratic formula for that. So negative b plus or minus the square root of b squared minus 4ac over 2a. 2a, a being 1. Okay, let me just double check my work here. Opposite squared. Hey, what have I learned? There's no x-intercepts. And that's great, right? When you know there's no x-intercepts, that means this graph could not cross over the x-axis. That's going to tell us a whole lot about the graph and about where the correct position is going to be. Right. Okay. So we have this version here. And now let's think about what happens as the limit as x approaches infinity. And I'll use the x plus 3 over x minus 1. Okay? Think about what happens here. And we kind of saw it as we did these limits right here. This part sticks around, but this part over here, this is going to be approaching 0. Why is it going to be approaching 0? Because you're taking 3 and dividing by a giant massive number. 3 divided by a giant massive number gets infinitely close to 0. So this part right here drops out, and all that really happens is, right, we're going to be approaching infinity. We're approaching this x. So, right, if I, what this tells me is that I have a slant asymptote at y equals x, right? Because this part goes away as I evaluate my limit. That's all that's left. That tells me where my slanted asymptote is going to be. Okay. By the way, if our remainder up here had been a quadratic, then this wouldn't have been a slanted asymptote. It would have been a parabolic asymptote. So our asymptote would look like a regular old parabola as we went through there. So the shape of it can really, the asymptote can be any shape we want. So if I'm looking at, okay, great, I got that slant asymptote. And I could do the other limit here. It's just kind of not really going to be helpful for me. I know it's going to be going down, but this doesn't really tell us a whole lot as to what happens here. It's not like when we're doing horizontal asymptotes that told us the number we were approaching, right? By just knowing that this portion over here disappears for really large values of x, you can just figure out your slant asymptote is the non-remainder portion. Okay, so we have that. Let's see, what else do we have? Oh, do we do cross? Cross, and just like we did cross the horizontal asymptote, we're going to check if we see if it crosses slant asymptote. And what does that mean? Well, there's our slant asymptote, y equals x, and there's our equation right here. So basically, can the slant asymptote equal the actual equation? And I'm not going to use this version right here. I guess I could use this version, but it's actually easier to use the divided version because you'll have this part cancel out. Can this part equal 0? No, it can't. So the answer is no. Okay, there's no time that this 3 over x minus 1 is going to equal 0. It might approach 0, but it's not going to actually equal 0. So let's take a look at our graph now. Now this coming down. Okay, we know it can't cross over the slant asymptote, so it's going to stay over here. It's going to be here. From our limits, we know it's up here. Again, we know it cannot cross the slant asymptote, so it's going to stay right here. Notice how this corresponds with the fact that we said there's no x-intercepts. Our graph has no x-intercepts, right? So we're all set with that one. Okay. These problems can have multiple vertical asymptotes. They can have open circles. They can have everything we've had before. It's just that the main difference is that instead of it being our infinite asymptote being this, it's going to be like this instead. Instead of it being like a horizontal asymptote, we're going to have it like this, or it's going to be curved like that. Let's look at another example of a slanted asymptote. Right? Okay, and here's one for you on that. Okay, so y equals x cubed plus 2x squared minus x minus 3 over x squared minus 1. Okay, now just to keep this in mind, right? Like we did before, we'd like to get to factor it first, but hey, if you're looking at that cubic, sorry, it's out of focus. Let's see if we can get to focus. Okay. If it's not going to factor, or if it's not easily going to factor, don't worry about it so much. I see that this is a higher degree than this, so I know I'm going to have to get my slant asymptote, so I'm just going to do the division now. Okay, how many times does x squared go in x cubed? It goes in x times, right? So those cancel, those cancel. By the way, I'm picking convenient examples so that they cancel. They don't always cancel, but they could. Right? Okay. And just make sure. Okay. So 2x squared minus 2. Subtract that. Negative 3 plus. Okay, so it's a negative 1. So right. So this is the same as x plus 2 minus 1 over x squared minus 1. Okay, and you notice how we didn't factor it before, like we didn't see if it factored it, and this kind of shows us like, hey, it wouldn't have actually kind of reduced at all here. This is x minus 1, x plus 1, so we can get our domain restrictions right there. So if there was ones that could reduce out, it would have been able to reduce out here later on as well. So you don't have to get too concerned about that, about trying to factor that at the beginning. So domain restrictions at plus or minus 1. Okay, as we're approaching 1 from the left here, again, you could use this if you wanted to. That's totally fine. I'm going to use the reduced version here for myself and just think about that. Right, so it's going to be, for these parts, that's approaching 1, that's 2, so it is 2, so it's 3 minus 1 over 1 to the left is like 0.99999, so it's negative a small number times 2. So that's going to overall be a negative small number. And it was already negative, so it becomes positive. So now we're approaching infinity. Okay. If we're approaching 1 from the right, x is still approaching 1, plus the 2 is 3, minus, okay, 1 from the right is like 1.01, right? So that's going to be positive small, times 2. If we look at it, hey, that's positive small, so this is going to become infinity, 3 minus infinity, negative infinity. So we can kind of see what's happening with our graph here, right? That it's going to be at 1. We're going to have our asymptotes. We're going to have a vertical asymptote at x equals 1, and it's going to be going from the left, from the right it's going to be going down, and from the left it's going to be going up. Okay, we'll do the same thing at 1. I'm sorry, negative 1. Okay, this part, it's just x. What's it approaching? It's approaching negative 1, so negative 1 plus 2 is 1. Okay, right, this excuse me, is negative 2. It's approaching negative 2. This part is approaching 0, but if it's not from the left, it's like negative 1.0001 plus 1, so it's negative small. Okay, so this is going to be infinity. 1 minus infinity, negative infinity. We see that that's also a vertical asymptote. Okay, I'm going to just do the other direction as well. Okay. And you should expect these to be opposites from each other because each of these zeros that we had here was a degree of 1, and you hopefully remember from last year's graphs, degree of 1 means that as you approach your asymptotes, they're going in opposite directions. So if you don't remember that, that's okay, right? But that's one of those things you can piece everything together. It does help you to make these easier. Okay. We also can see where our slant asymptote is. Our slant asymptote is y equals x plus 2. So I go up here, 1, 2, right, there's my slanted asymptote, okay, for myself. Okay, I forgot to find x-intercepts again, so let's do those x-intercepts. Okay, x-intercepts can be tough because we have a cubic here, and in order to find those, oh man, I might have to like hope it factors or whatever. So I'm gonna punt on that one because it's a cubic, and it could be like it's also a pretty high chance that they're going to be wacky x-intercepts. So I'm gonna hold off on that. How about we get the y-intercepts though? Y-intercepts we can get, that's going to be, or y-intercept 1, right? 0, 3, and that makes sense from what we have right here. That doesn't surprise me because I can see my graph is basically going to do this, right? I haven't checked to see if it crosses over yet, but just from all the basically it's connect the dots, and that seems like the most logical. Let's just see if it crosses the slant asymptote. So set the slant asymptote equal to the function. I'm going to use this version. Okay, these are going to cancel. And I look at that and I say, nope, that's never going to happen. All right, that's not true. You're never going to have a value where 0 equals negative 1. So there's no. And that helps because then I can look at my graph here, right? I can see that it goes like this, and that this one goes like this. So there must have been an x-intercept. There's probably just a really, really messy x-intercept. Those are super messy. A lot of times when you have these higher degrees, that's one of the things that when you do slant asymptotes, you don't have to show the x-intercepts because they just might not be usable. Okay.